Okay, so yeah. All right, so I guess it's recording now. I didn't have it recording. Uh, so, Math 1201. This is the lecture for Tuesday, November 24, and Wednesday, November 25. And this is the middle of chapter 10. And yes, the test will be concerning itself with the beginning of 7, the end of chapter 8, and as far as we can get in 10. I'm especially thinking at the middle point of 10 would be more appropriate to us, which is what I'm going to try to get to, at least in part today. We still have a lecture almost for sure live the following Tuesday, and Monday and Tuesday rather, and then live for sure the last Wednesday and Thursday, the last couple of days of December, December 2nd and 3rd. That'll be primarily a review for the final, cumulative final, of course. Finishing up 10.2, though, using the bootstrap sampling distribution to construct a 95% confidence interval, they say how similar they are. They don't really tell you the major differences. I suppose bootstrapping is used when you have difficulties finding certain points or allowing certain points, is probably a better word. And simulation will give you everything that's reasonable in that window, whereas bootstrapping only depends on what you have from your sample. Even if it's a pretty big sample, 157, you can't get anything else. But as you take means, the means start to collect very similarly to this. And that's due in part because we had a big sample. They become pretty much indistinguishable, even though they're not exactly the same. This, of course, is the same old one we've been seeing over and over again with a mean of 60.1 and a margin of error of 1.4. And luckily, we only have the one curve to look at instead of trying to pin it between the two that they're very, very fond of doing. Data cap window down here finds the confidence intervals, the interval rather, using the simulated sampling distribution centered at the sample mean, and sort the means just like before. And we're going to find the 25th largest mean and the 975th largest mean, because everything in between is the middle 950 out of 1,000. That's 95%, upper and lower bounds of the confidence interval. We did this before. We're also going to do it with bootstrap distribution. They've got the first one set up for a simulated sampling distribution. That's all ready to go. And all we have to do is to change the sims command to the boot command. And so let's keep the SDOM there, but each time down here we're going to have to replace sim with boot just to keep them separated. B might be good enough, come to think of it, but let's go ahead and type in boot every time to keep it separate from before, because we had the sims up here. And otherwise it'd be exactly the same. That could cause some difficulty, so we don't want that to happen. And plus they are two separate methods, so we'll try to get that in there. By the way, the hint did say, have you changed the variable to bootstom? Yes, we have. So let's get back here and run it. In fact, the answer is right below us, actually. And let's see, we actually got 4 different answers. Very nice. Yes, of course. So we have the simulated one, which is what I put my money on. That's a little bit more thorough, in my opinion. And that confidence interval goes from 58.81. And we're getting, I'm sorry, I'm not sure why it didn't work out. Oh yeah, we've got to range bootstom, not simdom. So I've got to make sure that comes out as a boot. Okay, so that's why they're the same. I noticed that these pairs are the same numbers. That's not supposed to happen. So let's go ahead and run it now, see what happens. And there we go. Still the same. Okay, well, not quite sure why that is. But the first pair of numbers are correct under the simulation. The one that's most important goes from about 58.8 to 61.5. Now, they're saying it should change up a little bit. This is more like 58.7 to 61.4. It slid back about, what, 1/10 of a point. I'm not quite sure why I can't get that to run. Let me just go ahead and submit it, and then I'll check the solution. I hate to do this, but I guess I've got no choice right now. And bootstom, got that already. That's what I thought I did. Yeah, so the script, and there must be something very subtle, and I hate to waste your time looking for it, but I just don't see any difference at all. So it says nice job, but yet the numbers don't come out the way they're supposed to. So let's shrink this down so I can get at it. And yeah, so anyway, Little glitch there. Sorry about that. Doesn't make me feel super confident about doing this stuff. Anyway, they did summarize. We got the better one was simulation, in my opinion, 58.8, 61.5. But notice how close it is. With the bootstrapping, only using the values that you have available, nothing else. Even though there are quite a few of them, it just shifted to the left 1/10 of a point. So let's go through a couple of these at the end to finish off 10.2 finally. And from our simulated confidence interval, we could also take a look at the margin of error, the distance between the upper bound and the mean. So the edge, upper edge, and the midway point of the mean, 61.51 minus 60.1 is 1.41. And before we got 1.39. Why didn't we get exactly the same thing? Well, random simulations have an element of chance. Each simulation will have some fluctuation. Absolutely, yes. It should be pretty close. This one is the right answer. The previous one was just an estimate. Not really, no. The code was a little different from the previous code. Well, that has nothing to do with it. And to finish this one off, we say from our bootstrap confidence interval, we could also take a look at the margin of error, the distance between the upper bound and the mean, which is 61.4, minus 60.1 is only 1.3, a little bit smaller. Why didn't we get the same exact margin of error? Well, we already said they're going to be a little different. And yeah, both resampling and simulations have that element of chance. And each random sample generated with these processes will have some fluctuation, absolutely. And they're only giving you a chance for one answer here. Don't pick B. This code is buggy. Well, that may be true, but that isn't the right answer. We need to fix it in the next section. I agree with that. Because we ran a few different lines of code simultaneously, no. They can run hundreds, thousands of lines of code and not worry about that. So that's it for that section, using bootstrapping to construct a confidence interval. Let's get to some that are a little bit more appropriate to ours. If I can get over there. And there we go, 10.3. Using the normal distribution. Now we're talking. Normal distribution to construct a confidence interval. This is what we're really aiming towards. It probably should have just started with 10.3. But sounded like other people had started chapter 10 too. So we could find something out of the beginning of chapter 10 to talk about. Okay, we've introduced two methods of creating sampling distributions, simulating and bootstrapping. We now will introduce one more method, modeling the sampling distribution with a probability distribution, and that's the normal curve. Extremely popular. So popular they called it normal. We used the normal curve way back in chapter 6 as a way to calculate probabilities in the population distribution. And not all of them are normal, but it seems like the vast majority are. But when they are, the normal curve gives us an easy way to calculate a probability. So we have the thumb length again, and we can pick the XP norm function to tell us the probability of the next randomly selected individual having a thumb length greater than, focused on the greater than, 65, for example. Now they refer to the central limit theorem, the normal bell curve. Turns out to be an excellent model for a sampling distribution of means. So even if it isn't normal, sampling distribution still becomes normal if you pick enough of them, like at least 30 or so. Especially when sample sizes are larger, it's even better. And everybody would use it anyway before computers were easily used. So what they've done here with a couple of commands here, the GFD histogram and GFDist, with a couple of things that you can read at your leisure, they've taken the sampling distribution of means, which means that they sampled a bunch of them over and over again, found the means each time. We didn't spend a lot of time. That's found in chapter 9. If you feel like reading a whole chapter on that, be my guest. But just to make it short for you, they've taken several distributions that come from the sampling, and that is come from the simulation part, which means they can just set the computer on autopilot and pick several different ones. I don't know exactly how many were on this, but the best part is they filled a bell curve over it, and it looks like a pretty good fit. It's a very nice fit. Sometimes it's not. We've seen a couple that weren't, but this one is. Anyway, using the normal model, and I can see they're back to the twin tower argument again. Let me hide that. The logic of using this normal model is exactly the same as using a simulated or bootstrap sampling distribution. We're trying to find out the range of possible population means that could have produced the particular sample mean we observed in our study, at least with a realistic probability, such as 95%. As they say over and over, you use it 100%, then you can pick anything at all. But what good is that? Not much, except for those theorists. In reality, there's no population mean. Here they go again, for which the sample mean is impossible. So yeah, you could pick negative 600 if you wanted to, and it's not impossible, unless of course the numbers had to be above zero, which they do. So you have to pick something close to zero maybe. But anyway, say that another way. It's the sample mean is possible, technically possible under any population mean, but we don't really care about that. We're looking for the most probable, as I try to circle it with my cursor. The sample means within the range of the most 95% probable sample means, then it's included in the 95% confidence interval. And here they go again, creating it inside out. But really what we're looking at is the center. They should put one big curve there and not put too much emphasis on the two curves. But that's just my opinion. They see things differently there. So many different ways to do this, but I prefer to find the simplest way if I could. I'm not really given that choice so much right now. The margin of error represents how far off the true population mean could be from our estimates. So yes, that's true. We've been saying that again and again. And so they've used sampling distributions. I prefer to look at it as a single curve, not two curves, two extreme curves. And so they talk about the 2.5% cutoff points again. So I'm kind of hitting an overview here. I'm not really very interested in their R graphics that they seem to be trying to parade around a lot, apparently. Subtracting the margin of error tells us exactly where the lower bound is, and adding it, we get the upper bound. Yeah, so here we go. A single curve. Amazing. I love it. Single curve. That's all we need. In fact, we have a very important empirical rule coming up. So with simulated and bootstrap sampling distributions, we constructed sampling distributions and putting the means in order and using cutoffs. We talked about all that before and getting the middle 950 out of 1,000. And we can find the confidence interval. Using the confidence interval, find out that margin of error, which is important. We like to know how big it is. But with a normal distribution, we will take a different approach. This is what's usually done, by the way, finally. The normal distribution is a mathematical model. There's nothing to order or count, but we need to find other things. And so a rough way is called the empirical rule. And so what it's saying is within one standard deviation of the mean. These are z-scores now. So one standard deviation above the mean, one standard deviation below the mean, and of course sitting right on the mean. We look at that little arrow here. 68.3%, a little more than 2/3, will be within one standard deviation of the mean. And one that's the most important one is the within two standard deviations of the mean. And of course that means as high as a +2 for z and as low as a -2 for z. So we're looking at this window here, which covers this arrow here. Now I know it's not exactly 95%, but they're going to go with a rounded number here, saying that look how 95 is close to 95.4. Yeah, it is kind of close. So that's the one that stands out within two standard deviations, is the one that we are interested in. So even before we know the standard deviation of the sampling distribution, we know the lower cutoff point will be about two standard deviations below the mean, and the upper will be two standard deviations above the mean. In other words, where z equals -2 and z equals +2. We'll make a refinement to that in a little while. But for now, let's just call it plus or minus 2. It sure is simpler. And here we go again with the, there's the main. Well, here's the main distribution. The light purple, ironically, is the main distribution. They're looking at the lowest possible scenario for some unknown reason. They've got a fixation on that, in my opinion. I just don't see it. And yeah, margin of error. Okay, whoopee. I said the same thing, but 10 times before. Anyway, let's get to the multiple choice questions. Recall that the margin of error we found, from both methods, was about 1.4 approximately. Which of the following are equivalent measures of this distance? As we are in 10.3 now, about the normal curve, check all that apply within 4 standard deviations. No, I don't see that that's right at all. B, 2 standard deviations. Yeah, that's pretty good. And 2 standard errors. Yeah, that's quite similar in some ways to standard deviations. You just have to get a square root of n involved and divide it, but that's essentially about the same as B. And then here we're just asked to convert from millimeters to centimeters. Well, let's see, there are 10 millimeters in 1 centimeter, so we would have to divide by 10. Go from 10 millimeters to 1 centimeter, which I could write on the screen, but I can't. So divide by 10, you get to 0.14 centimeters. So that's just asking you to convert to centimeters. No good reason for that. They just wanted you to do it. So those 3 are the ones that are correct. And you can check it out. If that went too fast for you, just check it out yourself and learn from your mistakes. That's something that maybe I'm stealing from you. I hope I'm not. Ideally, it's best for you to do this first, but I know we're getting in some difficult material, especially at the beginning of chapter 10. Was not very simple. So anyway, this one says the 95% confidence interval is roughly 2 standard errors above and below the sample mean. How wide is the confidence interval? Well, how wide across wouldn't be just 2, it'd be 2 on one side and 2 on the other. Let's take a look at the better sketch back here. 2 over here and 2 over there. 2 and 2 is 4. And they do have an answer for 4. There it is. It's D. It's not going to be 1 or 2, or certainly not 0. And 99 is a crazy answer. No way. Let's test the ideas. Let's apply it to the confidence interval we constructed. 60.1 plus 1.4, and that's 1.4 millimeters equal to 2 standard errors? And if so, how big would 1 standard error be? Well, the answer is clearly yes. And we just divide by 2. 1.4 divided by 2 is 0.7, and of course that's millimeters. Directly calculating the standard error using the central limit theorem. So we know how wide the confidence interval will be in standard errors, 2 on each side of the sample mean, a total of 4. If we want to know the width of the confidence interval in millimeters, we need to figure out how big the standard error of the sampling distribution is, and here they will give you the formula. I think they've given it to you before, but if not, here it is. The sigma of the y's, which is this sampling distribution, etc., will be take the sigma that's given and divide by square root of n. So that's the formula. Don't even look at the other ones. This is the one that we will be using for version C. The others are all off by a little bit. Notice we don't actually know sigma. What can we do in this case? Nothing. We are stuck. Oh yeah. Well, that's the way I felt in the beginning of chapter 10, but not quite. Let's see what the other ones might have to say. Let's see. We have this one over here. We can use the mean of our sample as the estimate of sigma. Absolutely not. The mean is almost never the same as the standard deviation. C, we can use the standard deviation of our sample, S, as an estimate of sigma. Absolutely. S pinch hits for sigma. Yes, it does. But the variance, no. You'd have to take the square root of that. That doesn't really help us. So there we go with C. And so, yeah, we estimate the standard error by taking S and divide it by the square root of n. So S over square root of n will have to do whenever you don't have sigma over square root of n. And the n just, that accounts for what's in your sample. So maybe the square root of 157. Cuts the number down to size to shrink it to fit for the center limit purposes for the sample size n. So they ask us to do it in R. That sounds like a relatively easy task, I'm happy to say. So we need to estimate the standard error given the fact that we have fingers, $ thumb, and we've written code to save the fave stats in terms of that, in terms of thumb stats. So what we need to do is to get over to standard error, and you can abbreviate anything you want. I'm going to just call it SE. I think that's what they might have done. And then let's go ahead and put the less than sign and the equal, actually the minus sign, that's the arrow that they have. And then thumb stats, and that's going to be, yeah, let's go ahead and do that. So thumb dot stats, and we can go ahead and say $SD, because we're after the standard deviation part of the thumb dot stats. Now that we have that in tow, we can divide that by the square root SQRT of 157. And I think that that's going to be it. We don't need to do anything else. So the hint was, of course, to review the formula for standard error if you're not sure how to calculate it. So yes, square root of n. That's all we have to do. So let's go ahead and run that and see what we get. Okay, didn't give it to us. Let me try again. Nope, I didn't ask it to do anything. So it looks like I have to ask it to print it out. So let's go ahead and do that on the next line. That'd be SE and thumb dot stats. Okay, dot stats, STATS, and $SD. I guess that's probably going to do it. Let's see if that makes it. No, I'm not having any luck tonight. Let's see about submitting it and just checking it out. Desperation time. Did you get the same as that? Yeah, that's what I thought I did. So let's just submit it and look at the solution. And here we go, thumb stats, $SD. Yeah, okay, that's what I thought I did. Maybe I didn't do it right. Okay, I guess I don't need to name it anything. Maybe that's my problem. So for next time, I guess I won't worry about that. So let's just erase that part and erase the other part too, and I don't want to waste your time with my mistakes. But a little bit of that is just part of the game, I'm afraid. Let's go ahead and run this now by Xing that out first and running it. There we go, finally. Okay, that's all it was. I just had a glitch there. Didn't have to define it by anything. That's just the way it was, so I thought I'd define it. Anyway, standard error, 0.696. That's, the original standard deviation we got divided by the square root of 157, which is around a 13, 12 or 13. And that's very close to what we thought it would be, 0.7. Remember, we talked about dividing 1.4 by 2, because that was 2 standard errors. We wanted one of them. And there it is, very close to 0.7. So that's nice to know. Let's go back to our original question. Given the sample mean we observed, what is the range of possible values within which we could be 95% confident the true population would lie? And that's the whole game here in the entire chapter. So let's see. Which of these describes how to figure out this confidence interval using the normal approximation? Well, let's see. Simulate sample means randomly generated from a normal distribution. Arrange the means in order. Look at the cutoffs for the upper 2.5% and lower 2.5% of simulated means. Well, that's not really the normal approximation. Bootstrap sample means, etc., but that's not really what we're doing here. Assume the cutoffs will be 2 standard deviations above and below the sample mean. Estimate the standard error using the central limit theorem, mean plus or minus 2 of the standard errors. Yes, that is C. So let's see if we can do that right here. And yeah, so we have that. Okay. All right. So yeah, I see what I did wrong. Okay, now I got it. If there is a next time, I'll be ready for it. Okay, so now using the standard error we just calculated, roughly 0.7, figure out the confidence interval around the observed sample mean. Is it close to the confidence interval we got from the others? We already looked at those. And so what we have to do is to look at the hint. Did you account for 2 standard deviations in your calculation? Well, let's make sure we do that. Thumb.stats $mean plus, we need to put in 2 of the standard errors. And notice here's where they call it SE. So I botched that one up. Let's just put in 2 times asterisk SE. And then subtract the same. Subtract 2 times SE. And let's run that and see what we get. This is about 58.7 to 61.5. Yes, this is quite close to what we got by simulation and what we got by bootstrapping, 2 other methods. But this would be the best method, because this would be the theoretical values that you expect to get in the long term. So this is the way that we always do it. The rest of it is just to double check stuff, I suppose. It's very similar to what we got from the others. They were off by just a little bit, perhaps. Using R to calculate the confidence interval. Well, we've been focused on the confidence interval for the mean, but it's important to note the mean is just one parameter you can estimate. There are many, many others: proportions, standard deviations, variances, etc., skewness, kurtosis. I could go on, but I'd better not. As you may recall, the simplest model, what we've been calling the empty model, only estimates one parameter, the mean. Remember, we use the linear model function to fit this one parameter model to our fingers data, and then we saved it as what they like to call empty model. We print it out by just typing in the name. So they pretty much set that up for us. And then they have a intercept 60.1. That was the mean, of course. And now we have a function called confintdefault, parentheses, takes a model as its input and then computes the 95% confidence intervals for the parameters of that model using the normal distribution. 95 is such a popular one, you don't even have to say 95. It just assumes you want it. I'm not quite sure how to change that to something different, but we'll worry about that if we need to. More and more they're just leaning on 95 in all the books, actually. Okay, so let's take a look. Calculating the confidence intervals of the parameters of this model using the normal approximation of the sampling distribution. Now this was an error because it says, oops, yeah, just click run, but the problem is this is in black. It should be in green. So I'm just going to simply erase it. I'm not going to recolor it or anything. I'm just going to delete it, and now we'll run it and basically just use what they said to use. So let's run it, and now it'll say, this is what we want. The lower 2.5% starts at, or borderline is at 58.7, the upper 97.5%, forming 95% in between. As you subtract the two numbers, that one goes to 61.5. And yes, they completely agree. This is not a simulation. This is, well, I hate to say exact, but this is from the theoretical model. So yeah, it's exactly from the theoretical model, so there should not be any difference. Simulations, you expect a difference. Ta-da! You may be thinking, why didn't they just lead with this? Yeah, I'm wondering the same thing myself. This is what all the other books do. Now, it's nice to go through simulations, even bootstrapping, but I would say put that afterwards instead of making everybody all unsettled, wondering what the heck's going on. Let's lead with the important stuff instead of burying the lead. Anyway, they could have just told you about this function like most of the other books do, but then you wouldn't have the rich understanding of what these numbers meant or what this function is doing. Okay, well, whatever. There we go. Let's move on and go to 10.4, a confession and the t-distribution. Okay, here's the confession. What they're going to confess. They've got a lot of things to confess to, in my opinion, but that's just my opinion. Try to make the best of it through this remaining part of the class. We're getting close to the end. Here's the confession. We've been kind of, but not really lying to you. We've been saying that a 95% confidence interval is roughly plus or minus 2 standard errors. And yes, I've taken a stats class where they use 2 the entire time. But this is back when calculators were really expensive. So that's what they just did. So people could just do it pencil and paper, I guess, or with their slide rule or whatever they did. But the real number, and you might remember that it was 95.44% for 2 standard deviations in either direction, standard errors. Well, if we want 95.00, we have to lower it from 2 down to 1.96. We won't worry about the details on that. We're not teaching tables anymore, so they'd be found in a table, but I'm not going to go any further than that. So you have to go plus or minus 1.96. That is one of the most important numbers in most statistics classes because that's a very typical request and a very typical formula. So we just get to use 1.96 dozens of times in a typical stats class. Here, we're going to barely notice it, I guess. There's one more thing, though. You may be wondering, why don't they just shorten the name of it? Well, you know, they can shorten a lot of things, but they just don't seem to want to. That's a good question. They call it confint.default. Tiny technicality here. They're saying, as you saw, the normal distribution isn't always going to be the best mathematical model. Typically is, but sometimes it's not. But when the sample size is large, you can assume that the sampling distribution is normal. Now, what is large? Over 30, over 40, over 100, I don't know. But the sample size is small, or if your sigma isn't even known and all you have is S, then we get into the classic case of what's called the t-distribution. You'll have more variation in your sampling distribution than Z can handle. The Z normal distribution won't be able to handle it all. Let's take a look at what they call the t-distribution, and we'll worry about the degrees of freedom in a little while. Notice the black distribution. This is the Z distribution. They're just disguising it as T with what they call infinity degrees of freedom. Degrees of freedom, if we haven't told you already, is n minus 1. So if it's infinity, okay, it's still infinity. But the point is, this is Z. Z is the black distribution, and T becomes Z as it gets bigger and bigger and bigger. But notice when T has got only 10 degrees of freedom, in other words, n was 11, very small, much smaller number, it's becoming flatter. It's like a squished pancake almost. 20 is a little bit taller up in the peak, but it's still got wider tails. The black tail kind of disappears, seems to disappear earlier, but the red distribution especially, you can still see it for quite a ways out there. So instead of being like 3 where it sort of disappears, maybe 4 or 5 before it finally disappears. Very similar, but it is different. And the two things you have to watch out for are smaller samples and a non-availability of sigma, having just S, which, by the way, is pretty typical. So that's why they like to get the big samples with computers. They often do, but that's the simulations, I should say. Raw data, you still have to go out and get yourself. Can't simulate that with, you know, that's a different story completely. Anyway, the figure is to show you that for a very large sample and large degrees of freedom, and minus 1 df degrees of freedom, the t-distribution looks like Z, because it is. It's a kind of a limit. It's pushed up into this little limiting deal here. And you can start to see it after n is like 100 or so. It's practically the same thing. Which of the following statements are true? Even more than 40, I guess you could say the same thing. And so we could go through some of these, some of which I've already given you the answers to. The normal distribution is in black. Yes, it is. The t-distribution with small degrees of freedom is depicted in black. No, more like red. The normal distribution, which I call z, is always the same no matter the degrees of freedom. And yes, that's true. That's a big advantage of z, is if you have something where sigma is known, that is, you know the standard deviation, if you collected enough history and things just don't change, like with me in the Forest Service and the tree data, so much of it was not variable, and we just call it sigma, and it made our life a lot easier. Yeah, we had to justify it, of course, but it was still easy to justify. But if you've got any real variability and you don't know what sigma is, then you have to break out the t-distribution, which I'm afraid is very common. And there's a little bit more work with the t. Going to number 4 here, the t-distribution is always the same no matter the degrees of freedom. No, you can see a couple of them right there, really 3 of them. T-distribution looks more like the normal distribution when we have more degrees of freedom, that is a bigger n, or n minus 1, to spend. That's interesting, you're spending your n. Well, that's one way of putting it. When you're going out and doing research and you're hiring people to do your work for you, yeah, you're spending money to get the data collected. That's true. But that's not the way we normally put it in a beginning book like this. But anyway, the t-distribution is more variable, often more variable, has wider tails, less clustered compared to the normal distribution. Absolutely, that was a big point I was trying to make, especially looking at the red one. It's not going to peak as much, and it's more wide. The area underneath all these curves, underneath all the curves, are exactly the same. It's 1 or 100%. It's just how is it spread out? Same basic bell shape, but there's different angles, so to speak. Of course, there's smooth curves, so I was kind of kidding on that one. Okay, last one. With a small number of degrees of freedom, that is small n, the t-distribution is more variable, wider tails, less clustered in the center. Yes, that's the red curve, absolutely. So lots of truths on that one. The t-distribution, like the z, or standard normal distribution, is a mathematical probability function. That is a good model for sampling distributions of the mean. It's just more variable, that's all. And I could talk about briefly the story of the t-distributions. It was called Student's t-distribution by Gossett. He had a unique position. He was like the chair at Oxford University in the statistics department, and he was also the head brewmaster for the Guinness Brewing Company. So that's a kind of a pair of jobs. And yes, he would take his beers home with him to sample them, I imagine. And they were small samples, and they were standard deviations. Maybe they're still getting the mix right or something. And standard deviations were not known. So he actually used that to test racing. I imagine he did it with chemistry and not gulping them down. But I'm not completely sure about that. But that's one of the many storied tales that I sometimes have time to talk about in a regular statistics class, but I just had to carve out the time here. Maybe I'll put that as a quiz question, see if anybody's watching this. Well, anyway, let's go back to the message here. Yeah, so if the sampling distribution was normal, or z, the margin of error would be 1.96 standard errors away from the estimate to get to 95%, approximately 2. We express this margin of error in terms of the units of standard error instead of millimeters. We call it a critical z-score. Plus or minus 2, plus or minus 1.96 is better. Let's try to think about what this distance would be if we use t instead. What would happen to t? Well, just take a look. It's a little bit more wide. So z in black would be like this, and t would be more spread out, so it's getting further to the outsides. And there we go, part A. And they're saying which one it would be. Would we have to draw boundaries further out or closer in? We just said further out, so yeah. And there's more sample means out in the tails. We have to go further out to capture 95%, 0.95 of the means. But closer in, that would be wrong. That's just wrong. I don't want to talk about that. Tired of false news here. So the function of xqt, called xqt, will take in the proportion you'd like to see in one tail and the degrees of freedom, if t is needed, and apparently it is. And we've got t right there, so that must mean t-distribution. They'll tell you the critical t-score and the margin of error in units of standard error. So what they're doing here is they're looking at the uppermost, well, actually the lowermost, 0.025, the bottom 2.5%. 1,000 minus 1 is 999, And that df is n minus 1, 999. So that's what's typed in. We're looking at this sort of orange area. Now we find the value isn't just minus 1.96, it's minus 1.96 and change. So there you go. That would be a more accurate number. We rarely need that kind of accuracy, however. Now if we put in 0.975, it'd be over here, wouldn't it? And it would be XQT 0.975, not 0.025 as we had back here. So there's the difference, 0.025 and 0.975. Same degrees of freedom. Do you think we would get the same critical t-score? And they're saying A, yes, it would be the same because the t-distribution is symmetrical. No, it would be almost the same. Critical t-score would just be positive because it would be on the right side of the 0. Yeah, that's basically correct. That's basically what we're looking for. So, yeah, so, right. So I think they got that one wrong because I've written down, they put down A, but I believe it's B. It's almost the same. It'd just be positive because we got a minus 1.96 and it should be a positive 1.96. So I'm going to make a notation change there. And then they're saying for C, it would be completely different. No way to tell what it would be. Oh, that's completely ridiculous. I'm insulted. So we can run this code. And the hint is just hit run. And this time it actually works, by the way. So let's try it. I have to X that out first for it to let me do that. And I do that, and they give me a picture. It's the upper 2.5%. That number looks like it's just a little less than 2, otherwise known as positive 1.96. They didn't happen to give us that right here, but we can see that that certainly makes a lot of sense. That's the upper 2.5%. The symmetry is still there. T is symmetry just like Z is. It's very similar in a way. It's just changed the sign. If you got the left tail, it's a minus number, negative number. The right tail, it's a positive number. And it happens to be the same absolute value, of course. So let's go ahead and take a look at that. So we did that already. And then now all we've done is taken the minus sign off. It should be exactly the same number, 2341. Yep, 2341. So that is the same. Let's take a look at the critical t-score for different sample sizes. This should be interesting. And I would actually go in the other direction. I'd start with 20, then go to 50, then 157, then to 500. They seem to kind of spoil the surprise a little bit early, but let's go ahead and change it up. All we really have to do is find the degrees of freedom. This is n sample size. We want n minus 1. What is 500 minus 1? Hope you don't need your calculator. And 157 minus 1, 50 minus 1, and 20 minus 1. So that's really all they needed to do. So we can go ahead and run that and see what we get. We can take a look at all the previous plots. There's actually a better picture down below. Well, actually, no, they didn't show the picture. We get the picture here, and we can see the numbers coming up. So here we looked at the sample size 500. That's very close to the bell curve. That's, in fact, you can see it down here. 499 degrees of freedom is 1.96. Now, the other numbers may have changed a little bit. Notice there's 2341, that's 4729. But the 2 decimal places, it's the same. So that's the important thing. But then we get further and further away as we have less and less degrees of freedom. So looking down here, that's a 1.97. It's getting bigger. It's moving towards the right a little bit. As I go to the third one, which was 50 or 49 degrees of freedom, now it looks like it's past the 2. In fact, you can verify it down here, 2.01 to 2 decimal places. Typically, T gets 3 decimals, though, so I'll go to the last one, which is only 19 degrees of freedom. This one's getting flatter and flatter, a little harder to tell, because I think they keep changing the scale. Well, they didn't. But you can see as you kind of put an animation on it by clicking them, it is getting a little bit lower, and the tails are getting a little bit wider as you go further and further away from Z. So now we're out to 2.09. It's definitely further than the 2, as you can see now. So the degrees of freedom, especially when it's a smaller number, it really does make a measurable difference. But once you get to past about 100, you can hardly tell the difference at all. Most books used to say 30, but anyway, they because technology is so easy to use nowadays, they just go ahead and say use T no matter what, unless it's like beyond 1,000 or something. Then even they don't waste their time probably with that. What do you notice about all these critical T's? Well, let's see. They're all around 2 standard errors, or they're closer to the critical Z when the degrees of freedom is larger. I don't see anything wrong with either one of those. They're all around 2. You can see the numbers. And then all closer to the critical Z's when the, yeah, we just mentioned that. Critical T's are bigger when the sample size is smaller. because the sampling distribution is more variable, further away from the z. So that's kind of going in the wrong direction, like we just did. All of them are true. Yeah, all of them are true. Absolutely. So that's basically what we're looking at here. So let's see here. We're at 10.4. Let's zoom up a little bit more. And now we have the function confint t uses the t distribution to estimate the margin of error. It'll adjust for the size of your sample automatically. And I guess, well, let's see. The function confint default uses z, which does not change with degrees of freedom. So that, yeah, default is the z, I guess. So you have to type in the word default, unfortunately, though. Okay, let's see. Given that the t distribution is more variable and the margin of error will be slightly bigger to capture the middle 95% of the sample means. And so that's not really a question. I'm kind of confused by that, but A says confint results or result in slightly larger confidence interval than confint default. Yes, t is bigger than z. It's more spread out. Yes, smaller is wrong. T, which is what we're talking about, is bigger than the default, which is z. What would be a slightly bigger confidence interval? What would a slightly bigger confidence interval mean? It's just simply wider. That means all the bounds are changing. And so we would have to deal with the value being smaller. Let's just compare them. The z, which was at the largest number possible, yeah, the number is smaller. Yeah, the positive 1.96 is definitely smaller. So yeah, the lower bound, that'll be smaller too. So yeah, that'll be how that goes. And yeah, anyway, I'm not quite sure what I did wrong with that. Looks like it'd be smaller and that would be bigger. Okay, there we go. It's A and D. Okay, so as I compare the t here, going back to the picture, the t's, especially as we go out to the further one, it's gone further away. So it's gone away from the z. The t values are larger in absolute values. So you've got a plus 2.09 and a minus 2.09. It's just wider. It's just wider. I think of that in terms of wider. And so they think of it a little bit different, is that they push the lower bound back further, so it is smaller, but it makes it wider. And then the upper bound would be bigger or larger. So A and D are correct. Try out both these functions in the window below. Is the confidence interval based on the t distribution larger? Would better be. So we have confint dot default and then empty dot model. And let's see, it looks like write code to calculate it based on the t distribution. That's going to be about the same thing. All we have to do is drop out default. So let's go ahead and copy this. I'll just put it right directly below. And I'll just erase the default because confint assumed it was t. So let's just try this and let's take a look at the hint. Perhaps the hint says use confint for t distribution. Yes, that's what I did. And the dot default is z. It's just their way of saying that. Okay, so now we see a change. And maybe this is, yes, it's exactly the same. This is based on the theory, so it isn't based on any kind of simulation. And looking at z, which is always the big one. Z is always the big one. It has a kind of a distribution, a 95% confidence interval that goes from 58.74. And then as this has gotten narrowed, a little bit narrower, that's a little bit of a surprise. Yeah, I'm not certain why that happened, but the t distribution is actually a little bit, it's wider. I'm sorry, it's wider. Yes, this has gotten further away towards the left of the 58.73. It's just look at the numbers without even rounding them. So 0.72 goes further to the left. And then over here, 61.46 truncated compared to the 61.47. You can see it's moved to the right a little bit. It's just gotten wider. So I'll try to show my cursor what I'd like to show with a pen, but I can't. So that's a wider distribution. Not by much at all. So that is surprisingly close. Maybe that's the model with 157 in them. That's a big enough sample size that you're starting to lose the difference between t and z. With small sample size, which is what the t distribution had been used for classically with hard-to-get sample sizes, the ones that cost a lot of money, take a lot of time to get, and you can only get maybe 10 at the most. That's where t is always shown more clearly than z. Anyway, using the t-distribution to approximate the distributions lead to a slightly wider confidence interval. And for samples that are fairly large, it doesn't make a huge difference. So I've graded many papers where you'd have to take it out to the second or third decimal place to see any difference at all. And that round-off error was quite important. So anyway, plus or minus, about plus or minus 2 standard errors from our estimate is our 95%er. That's the big news. If you have a fairly large sample, it won't really matter if you use T or Z, especially if it's beyond 157 or so. If you have a small sample, though, it will matter a bit more, sometimes a lot more if you have a very small sample size. So if you have a small sample size, don't use Z. Z as the default. Just use the regular confint T. So that is definitely A. So yeah, just use confint T. Confidence interval must be it. It seems to say T. It's a coincidence. Gives you the best estimate regardless of the sample size parent. They have already figured out what n is. You don't have to type that in. But sometimes you may just want a lower bound of a confidence interval or just the upper bound. That could happen, especially in a one-tailed test that we don't really have time to do. Sad to say, very basic part of stats that we can't cover. If we tell you the function confint returns a vector of 2 numbers, the first is lower, and you could probably figure out how to get just one or the other, but the code is such that the number 1 gives you the lower bound and number 2 gives you the upper bound. So you could split them in half and just look at one or the other. They just happen to be running them back to back. The hint says just click run, and yes, that actually works. So let's go ahead and run that. Run. And there are the numbers, 58.72, 61.47. That's exactly what they got. But you can look at them one at a time. But instead of saying lower and upper, you have 1 and 2 in the natural order of things. 1 is the lower one, 2 is the upper one. Okay, so confint empty model 1, lower bound, and confint number 2, upper bound. So let's go ahead and go to the next one and see if we can get somewhat into 10.5. I do not plan to finish it, but this material is moving a little bit faster now that we've gotten from 10.3 on. I'd have to say definitely emphasize 10.3 on in this material because we're getting into real statistics now, not just pretty R diagrams. To summarize where we are, confidence intervals are constructed around our parameter estimate, usually the mean or the sample mean. In case of the empty model, it's the sample mean. They like to call it empty model, whatever, the basic model, I guess. What a 95% confidence interval says that we have likely values. That, of course, contains the true parameter. The interval contains the real parameter and the mean of the population. There are others we could do, but the mean is the easiest one. The interval is typically symmetrical. Whether it's Z or T, we have symmetry involved. Not all of them have symmetry. I just did a workshop yesterday that was for Chaffey College. That was a non-symmetric distribution, the chi-square distribution. We will not have time for that one either, and that's usually part of a basic statistics class. The size of a confidence interval tells us how much fluctuation there is in our parameter estimate. Yeah, there's fluctuation. That's the margin of error. And we could do it in original units or in terms of the number of standard errors, which I kind of like a little bit better. But either one will work. Larger the standard error, wider the confidence interval. They go together. So we realize the confidence interval is determined in part by n, or n minus 1 degrees of freedom, and of course the real standard deviation of the population. That's the sigma, and here we have n minus 1. We convert it to n. Consider these abstract situations. If we had a variable called a that's highly variable, and another variable called b that's less variable. I've got a cat that wants to sit on me now, but I can't let her do that right at the moment. Sorry about that. Anyway, b is less variable than a. If we estimate the mean of each variable, which estimate would have a wider 95% confidence interval? This seems like an obvious one to me. Here we have a that is highly variable. What else would it be? It would be equal. Oh, no. Wide means wide. That's what it means. So anyway, let's say we calculated 95% confidence intervals for those means of A and B. And we have n is 100. Very nice. Which confidence interval will be wider in terms of standard error? Well, of course, A would be what we're looking for. But C, it says they'd be equal in terms of their standard error. That's true. Whether it's 1.96 or 2.09 or whatever, both would be around 4 standard errors across. Using the standard error as a ruler adjusts for the variability in the population. So and I didn't read this. You have to read the problem. That includes tests about the number of standard errors. Now here, if you read it too quickly, you're going to go for A. But no, we talked about standard errors. So C says we're going to standardize it about plus or minus 2. And D is clearly wrong. That's just a bad answer. Let's say we took a small sample of A and a large sample of A and calculated the mean of each sample. For which sample would our estimate have a wider 95% confidence interval? Well, the wider one would be with like the 10 versus the 20. Remember, we had degrees of freedom of 10, which is like 11, and 20. And we saw that was wider with the smaller samples. That's a fundamental idea here. That's something that might even be a test question. You never know. But if people were to get that wrong, you kind of miss the whole point. So that's the one point we're trying to get. Disguised in all this R stuff, we do want to say that with small samples, we have wide variability. And the bigger the sample size is, the better it is. It becomes more like Z, becomes a little tighter, more narrow, and that's a better thing for everyone. Okay, yeah, so not equal, no. Those are wrong. Now, why would a small sample be more likely to produce a wider confidence interval than a larger sample? I'm going to skip ahead to B. Because the standard deviation of the population divided by a smaller n would result in a bigger estimate of the standard error. Exactly. Divided by a small number, the number is bigger. So you have to share amongst 2 people versus sharing amongst 10 people. Guess which one is better for you, especially if you like what you're sharing. And C, because smaller samples are more variable, so the sampling distribution would be wider. Absolutely. And notice it did say check all that apply. Because the critical distance in terms of standard error, the t-score, would be bigger with small samples. Yes, that is true. What about A? Because the small sample would be more likely to overestimate the standard deviation of the population. So they let off with the confusing one first, so I put it last in my discussion. That one just kind of misses the point. Units of the confidence interval. The actual size of the 95% confidence interval is here. We've already found that. Lower 2.5% and then upper 2.5% represented by the bottom 97.5%, by the way, and that's your confidence interval right there. What are the units? Well, of course, we were talking about thumb length. So, no, the units are not thumbs, they're not number of students, they're not standard errors, not percent. No, we're still back at millimeters. That's kind of a trick question. They love their Twin Towers again, so we're going to take one last look, hopefully one last look at this stuff and see if we can fill in some of the blanks here. Okay, so what we have is A. What is A? A is the mean of the smallest possible viable population that we have. And that number was, as you can see, close to 58 point something. Yes, that's it, the lower bound, which causes its own little confidence interval. And just to follow it up, the B is doing the same thing on the highest possible one, and its mean happens to stretch out to form its own confidence interval, and that's 61.48. Now, the other ones, now we're talking about the real stuff in the middle. C, well, that's going to be the margin of error, 2 standard errors below the estimate. Yes. And D is the same. As you can take a look, D is the same, but it's 2 units, 2 standard errors above the mean. And so that's that one. And then, of course, 60.1, the estimate for our sample, which was the sample mean. I'm so used to seeing that as X bar. They like to call it little b0. They just have a different style. Match the following concepts to the notation. And yes, you should probably try this first. If you want to pause the recording and do it yourself, please do. This is meant to be kind of a double check, not meant to just guide you through. At least at this point, you should kind of be picking up stuff. So we're into the more mainstream material now, believe it or not. Match the following concepts to the notation. So the lower bound for the confidence interval. Well, what they're after here is the lower bound of beta 0. That's the actual, I call it mu, the actual mean. The upper bound, same thing, except that's the upper bound of beta 0 again. Margin of error in terms of standard error. Okay, that's going to be the critical t-value. Yep, that's going to be in terms of the standard error. Yes, we attach that to the units of the standard error. And here's the standard error. They're trying to break it up into 2 pieces. I think of it as just one big clump personally, but that's the standard error. Since we don't know sigma, if we did, we'd be using z. We've got s, and we have to divide by square root of n, whether n is large or small. Putting that together gives us the margin of error together, but the estimate from our sample, that's the B0. That's the X bar, I guess you could say, the sample mean. Okay, getting close to the end here. Match the following concepts to the R code, assuming that these lines of code have already been run, and so we have thumb.stats, which has come in from the favstats with the variable tilde thumb from the data set called fingers, and then they're going to try to find the confidence interval, the T version of that, because it's not default, of what they call the empty model. So that's what we can try to get a hold of here. And so the lower bound would be confint empty model with the 1. Remember we used the 1 for the lower number and the 2 for the upper model? Well, guess what? That's the 2 for the upper bound for the confidence interval. Lower bound gets the 1, and the upper one gets the 2. Margin of error in terms of standard, in terms of units of standard error rather, will be the XQT command, 0.975, and then we put in the degrees of freedom and all that. I don't think we did very much with that, but just go with it. That could be the last one you put in if you weren't sure. Now the standard error happens to be the one that divides by the square root of n, but let's see, we've got the square root involved. There it is. There's a square root right here. So that's a very likely candidate. Thumb.stats, standard deviation. We divide by the thumb.stats with the n involved. This one you have to tell it to do the n or it won't understand you. And the estimate for our sample is the one with the thumb.stats and with the mean as the variable. So that's the estimate. So this is going into the R code, which is what we are required to do, tasked to do, so to speak. How would you find the margin of error approximated by the t-distribution? Check all that apply. Well, let's see. We've got B0 minus beta 0. That could be the lower bound. Yes, that's one way. That's not the way I would think of it, but it happens to be true. Beta 0, upper bound, minus B0. Yes, that also works. That's the Twin Towers approach of explaining this stuff in a more difficult way. Critical t times standard error. Now we're talking. This is what I'm used to. In fact, especially this one, D. So far, they're all winners. Take the sample standard deviation, that is S, over square root of n times the critical value of t, formerly found in tables. Now I'm going to skip ahead to F. Beta 0 upper bound minus beta 0 lower bound divided by 2. Well, okay, that one happens to work. Yeah, that happens to be true. You could find the margin of error, which is half of a confidence interval. So yes, you'd have half of that. Now E forgets to divide by 2, and that's why it's the only one that doesn't work. Now we have a video, and this is a good place to pause it in the middle of 10.5. I haven't watched the video, but I'm sure it's good. The videos seem to be a little clearer at explaining things versus some of the text, which perhaps I'm emphasizing too much, but they seem to get all their questions from the text, so that's why I'm doing it, even though it's not my first choice. So go ahead and watch that video. And so, of course, we will have a recorded lecture on Tuesday, office hours still on Wednesday, day before Thanksgiving, and we'll be back. I'm 99% sure it's going to be live the Tuesday before finals week, and then Thursday for sure it's going to be live. So it looks like back-to-back live lectures during the last week before finals. I'm still working on your tests. By the time you watch this, I hope I'm done with the tests. I'm doing your class first. I've just been bogged down with all this other stuff to do. So yeah, I will get to that as soon as I can. Well, meanwhile, I've rambled on too long. Shouldn't make these videos too long. So we'll have more on Chapter 10 and any other missing items that they seem to think were important for the final. And it will be a regular final, yes, it will. There's no special projects or anything like that. And I'll have more information on how to handle the review quizzes, but I have to get the test graded first. So I'll probably pick and choose problems for the review quizzes so you can kind of still look things over. Looks like virtually all of 10 will be covered, though, so you can kind of halfway plan on doing all of the review quiz for 10, but nobody wants to do it yet. Okay, I guess that's all I got for you, so we'll talk to you later.